In this lecture, I'll be discussing disk input-output and discussing many of the physical properties that come into play when attempting to schedule a hard disk drive for access by multiple programs. In particular, I'll talk about disk attachment, talk about some of the properties of magnetic disks, discuss disk addressing, discuss partitioning, and introduce solid-state drives. I'll begin with disk attachment. Disks are attached to the motherboard via some kind of cable, and the exact type of cable depends upon the bus in use on the system. There are several different types of bus, which are implemented by different chips attached to the motherboard on the different computer systems. One common bus that was widely in use until the early 2000s on consumer-grade hardware was the Integrated Drive Electronics, or IDE bus. This has been since backronymed Parallel ATA, or PATA, but consisted of 40 to 80 ribbon cable connecting to a 40-pin connector to provide 40 simultaneous parallel channels of communication between the motherboard and the hard drive. Enterprise-level systems of that time period typically used SCSI, or Small Computer System Interface buses, which consisted of a cabling of 50 to 80 pin connectors between the hard disk and the motherboard. SCSI also defined a standard set of commands, a standard protocol, for interfacing with disks, CDs, and other types of storage devices. This protocol was useful for recordable CD media and DVD-ROM media, and was implemented on the ATA bus using the SCSI protocol in a system known as a TAPI, or ATA Packet Interface. Now, in modern times, serial interfaces between the motherboard and the disk have replaced, for the most part, the parallel interfaces. For ATA-style disks, we have serial ATA, or SATA, which replaces the 40-pin connector with a 7-pin connector. Still uses the same protocol, either ATA or a TAPI protocol. And serial attached SCSI, or SAS, which uses the SCSI protocol over a narrower channel consisting of 26 to 32 pins. Both of these new serial attachment mechanisms support higher bus transfer speeds, enabling theoretically faster devices to be attached to the motherboard. This does not necessarily mean, however, that the disks have gotten that much faster. Now, we still store large amounts of information using magnetic disks. These are metallic or glass platters that are coated in a magnetic surface, and a stack of these platters is rotated at high speed by an electric motor. A stack of heads moves back and forth across the platters, altering the magnetic fields in order to read and write data. Moving the heads back and forth results in seek time, and waiting for the platter to rotate around to the correct position results in rotational delay. Historically, magnetic media were addressed by geometry. The smallest addressable unit of space on a hard disk is called a sector, and this is typically 512 bytes, at least on older disks, though other sizes have been used and newer drives go up to 4 kilobytes. Tracks are circular paths at a constant radius from the center of the disk, and each track is divided into sectors. One head reads from a single track on a single side of each platter. When you stack multiple heads up, using multiple tracks on the various sides of several different platters, the result is what's called a cylinder. And historically, accessing disks required accessing the particular data locations using cylinder head sector, or CHS geometry addressing. As disks grew larger and faster, however, this type of addressing scheme became limited, and so logical block addressing was put into use, and it's now the standard today. Logical block addressing, or LBA, gives each block on a disk its own logical address and leaves it up to the disk firmware to convert the logical addresses into physical locations on the disk. Current standards with logical block addressing on ATA will allow enough space for disks up to 128 pebibytes. Operating systems normally implement these 48-bit addresses using 64-bit data structures. Thus, operating systems that support 64-bit disk addressing can generally support hard disks up to 8 zebibytes of data, assuming we're using 512-byte sector sizes. Now, regardless of the size of the disk, it is convenient to partition the disk into multiple sections so that we can isolate data from each other. We can isolate the main partition of the operating system from a partition we would use for swapping out pages of virtual memory, for example, and we can isolate that from user data. Also, with early hard drives, it was convenient to isolate partitions so as to minimize seek time by making it such that the head didn't have to move as far in order to access data. Now, there are two types of partition table, or data structure that resides on the disk to indicate where on the disk the different partitions lie. A common partition table type that's in widespread use today is the master boot record-based partitioning scheme. And the way this works is that the BIOS on the system, the basic input-output system, actually loads the first 512-byte sector from the boot drive at boot time, and code stored in that 512-byte sector loads the rest of the system. Also within that sector is stored the partition table, which is called a DOS-style partition table. And the DOS partition table still uses legacy cylinder head sector addressing, supports a maximum of 4 primary partitions, one of which can be an extended partition with logical drives in it, and supports maximum partition sizes and maximum partition starting addresses at 2 tebibytes. This is the default partitioning scheme for Microsoft Windows and most Linux distributions. However, as hard drives become larger and grow past 2 terabytes, the GUID partition table, or GPT, starts to be used. This is a larger partition table that can support disks or partitions up to 8 zebibytes in size. For compatibility with old partitioning tools, and to prevent old tools from overwriting sections of the disk and seeing it as free space, a protective or dummy master boot record is retained at the beginning of the disk. GPT is the default partitioning scheme in Mac OS X, is an optional partitioning scheme in Linux, and is supported in 64-bit versions of Windows 7, Windows Vista, and Windows Server 2008, provided that the system uses the Extensible Firmware Interface, or EFI, instead of the legacy BIOS interface. For Linux, the Grub2 bootloader can use a legacy BIOS interface, but it requires a dedicated small partition on the hard drive in which to store the rest of the bootloader. Now, hard drives and magnetic media are used for large quantities of space because of their relative low cost. When high performance is required, we prefer to use solid-state drives, or SSDs. These drives have no moving parts, which makes them generally faster and less subject to physical damage than mechanical hard disks. Most of these SSDs use NAND flash memory to store data, and this is a storage mechanism that's based on injecting or removing an electron from a flash cell. Injecting an electron into a flash cell changes its state from 1 to 0, so this is backwards from what one would expect. An empty flash cell actually has a state of 1 instead of 0. The membranes through which this electron is injected and removed eventually wear out, typically after anywhere from 100,000 to 1,000,000 cycles. Furthermore, the electrons tend to leak out over long time periods of many years, causing flash to lose data, which makes flash-based memory systems unsuitable for long-term backups. In this diagram, we can see how a solid-state drive using flash memory works. Blank flash memory stores the value 11111111. So we have all ones here. If I want to write the value 10010100, I have to pop electrons into the second, third, 5th, 7th, and 8th flash locations, those bit locations. I'm pretending we only have a byte here. If later I wish to change that stored value to 10100011, I must first erase that block of flash memory before I can program the new data value. Generally, I must erase flash memory in the size of an erase block, and this is typically 4 kilobytes. Waiting for this block erasure procedure causes something called write amplification, where successive writes to an SSD become progressively slower. To avoid this problem, we typically erase the SSD ahead of time whenever space has been freed on it. And there's an ATA command called trim that facilitates this process. One other issue that has to be dealt with SSDs is the fact that each cell can only be written to and read from, or generally written to, erased and written to, a fixed number of times. This is typically between 100,000 and 1,000,000. So to spread out the writes across the entire SSD, the SSD moves data around the drive as files are updated, and it also reserves a certain amount of free space unused so that that free space can be swapped in and out with space that's in use later. This process, called wear leveling, has the advantage of dramatically increasing the useful life of the SSD and reducing write amplification whenever clean blocks are made available. However, in order for the write amplification reduction to be effective, the operating system and the underlying file system must support the ATA trim command, and furthermore, it's impossible to ensure that the disk is secure against forensic data recovery because it may not be possible to overwrite and properly erase the reserved cells of memory that have been taken out of service. Thus, a used solid-state drive should be physically destroyed instead of attempting to resell it, which can be an issue because a solid-state drive has a higher upfront cost. So in summary, disks are attached to the system via some kind of bus. The newer bus styles are SATA and SAS. These modern disks are addressed using logical block addressing. They're partitioned either with DOS partition tables or GUID partition tables. GPT use will increase as the size of disks becomes larger owing to the limits of the DOS partition table. And solid-state drives offer higher performance at a higher initial cost, subject to the requirement of wear leveling, and subject to not being able to be safely resold due to the inability to forensically secure the data on the drive.